Some students have asked me some questions over the last few days, so I'm making this video for everyone to be able to go through and review and benefit from these solutions. So the first question I was asked was from section 8.1, and it was asking why is the claim here p is less than 0.5 versus p being less than 0.37 from the 37% listed in there. So in this problem here, there's a claim that a minority of adults would erase all of their online information if they could. Someone wants to go through and test this claim using a hypothesis test. So a software firm wants to go through and see whether this claim is correct. So they go through and sample 525 people, and of those 525 people in the sample, 37% of them agree that they would go through and erase all of their online information if they could. And so the claim here is saying that a minority of adults would erase all of their online information if they could. So the way we want to go through and interpret the word minority as meaning less than 50%, the term majority goes through and represents more than 50%. And so by stating a minority, that's like saying less than 50%. And since the claim then does not include equality, but it includes inequality, it's either saying less than or greater than. In this case here, minority is referring to less than 50%. Our claim here is going to go through and be represented as p is less than 0.5, and since this claim does not include an equal sign, it has an inequality, it's going to become the alternate hypothesis in this problem. We are testing the null value then, since the null always has to include equality and contradict the alternate hypothesis. We use the same number of 0.5 and set our null equal to 0.5. Our p hat from our test statistic computation is going to be 0.37 because that's coming from the sample. That p hat variable in the test statistic formulation is going to be coming from the sample of 525 people. So we're going to need that sample size and that percentage here in computing the test statistic. We're not told what the alpha is in this problem, but we can see that this is a left-tailed test because this inequality looks like an arrow pointing to the left. We're going through and we're working with a percentage here, so it's telling us we're working with a proportion, not a mean or a standard deviation or a variance. And so we're going to be using the z distribution. It's a left-tailed test, and so depending on what our alpha is going to represent the area of this critical region. If we go through and compute our test statistic, and suppose our test statistic is landing in this red region, then we would go through and we would reject the null and conclude that indeed a minority of adults would erase all of their online information if they could. But suppose our test statistic landed outside of the critical region, then we would not have significant evidence to go through and support this claim. So until stronger evidence is found, we would go through and assume that it's 50-50. The next question I received was from section 8.3, and the question was asking, why is the confidence level for this 98%? In the problem here, it mentions a 0.01 significance level, so let's go through and see what's going on here. So we're told that 12 different video games showing drug use were observed. The duration times of drug use were recorded, with the times in seconds listed below. Assume that these sample data are used with a 0.01 significance level in a test of the claim that the population mean is greater than 85 seconds. If we want to construct a confidence interval to be used for testing that claim, what confidence level should be used for a confidence interval? If we found this confidence interval to be this value, then what should we conclude about the claim? Okay, so in this problem here, they went through and they did a hypothesis test. They tested the claim that the population mean is greater than 85 seconds. So it's important to go through and highlight that claim. Now let's just run through the hypothesis test and see what they did. So we can state the null and the alternative hypothesis. And then the claim, we're told that the population mean is greater than 85. So the claim does not include equality. It includes a less than or a greater than. In this case here, it's greater than. And so our alternate hypothesis is stated here as the claim. Our null always includes an equal sign, and so I'll be going through and using that same value. Now, it's important to note that with our alternate hypothesis having this inequality, we can see that it's like an arrow pointing off to the right, and so it's a one-tailed test. It would be a right-tailed test because it's like an arrow pointing off to the right. And in doing that hypothesis test, we would have our significance level here, which is the same thing as alpha, being the area in the critical region. We're testing means here, and we don't know the population standard deviation, so we would be using the t-distribution instead of the z-distribution. And in this hypothesis test, it's a right-tailed test with an alpha of 0.01. But if we want to get the same results using a confidence intervals are always two-tailed. And so we have to go through and double our alpha. And to make sure that this area is staying in the same spot, we don't want to go through and just half this to be like 0.005, because that would go through and shift our critical t value on over to the right. We want to keep our critical t in the same place, and so we have to double alpha. And so what that looks like is we just use symmetry and create an equal area on the other side. We can change our critical values to being, instead of the t sub alpha, we can do the alpha over 2. And so now, to figure out the total alpha for the problem, we add up the total area of this critical rejection region. So we've got 0.01 plus 0.01 gives us 0.02. And so this is our alpha. We can go through and determine our confidence level by going through and using the formula that it's equal to 1 minus alpha. And so if we just subtract this 0.02 from 1, we end up with 0.98, which is 98% going through and representing what the confidence level is if we're using a confidence interval. Again, because confidence intervals are always two-tailed. We cannot have one-tailed confidence intervals. See, the next question I got was from section 8.4, so another hypothesis testing problem. And in this problem, the student was a little unsure of how to go through and set up this problem. So let's go through it together. We're told that the piston diameter of a certain hand pump is 0.6 inches. The manager determines that the diameters are normally distributed with a mean of 0.6 inches and a standard deviation of 0.006 inches. After recalibrating the production machine, the manager randomly selects 23 pistons and determines that the standard deviation is 0.0043 inches. Is there significant evidence for the manager to conclude that the standard deviation has decreased at the alpha equals 0.05 level of significance? Okay, so what we want to do on this problem here is first go through and just analyze the situation. So it appears that the manager a while back has determined that the standard deviation for these hand pumps is 0.006 inches. So this is what the believed value is. So that the status quo value here for the standard deviation here is this value. This is what the population, hey kitty, stay down. The population believes that the standard deviation for these units here is equal to this 0.006 inches. But in going through and gathering some data and taking a sample of 23, the standard deviation was not that 0.006, it was less. And so the manager wants to go through and do a hypothesis test to see if the status quo value or the believed value of the population standard deviation should be lowered or should be decreased. Oh. Artemis, say hi. Okay. So let's go through the setup here. So again, it's a hypothesis testing problem. We want to go through and figure out what is the claim in this problem. And in going through and reading on through, we can go through and we're trying to test here whether the standard deviation has decreased. So we want to know whether the standard deviation is less than this 0.006 value. So in testing population standard deviation, we're testing this claim sigma. And our claim here has the decreased, so this implies a less than. And so our claim here is going to become the alternate hypothesis. It is a less than value, so it's a one-tailed, a left-tailed test in the situation because the inequality is pointing off to the left. Our alpha is 0.05, and so the area to the left of our critical value is going to be 0.05. And so we have some chi-square critical value. I say 1 minus alpha here because the chi-square distribution goes through and represents area off to the right. And so if alpha is 0.05, the area to the right of this chi-square value is going to be 1 minus 0.05 or 0.95. We want to go through and figure out what that critical value would be. And so in the assignment, the last page includes the chi-square distribution. Let me just go through and jump forward to that. And so in the chi-square distribution, focusing on the left for now, it goes through and it gives us the area to the right of the critical value. So since we have a left-tailed test, the left tail has an area of 0.05, while the right tail has an area of 0.95. And so since this only tells us area to the right and there's no symmetry with the chi-square distribution, we want to go through and do that 1 minus alpha and say, okay, we have an area of 0.95 to the right of our critical value. And in the problem here, we had a sample size of 23. If we go through, though, and subtract 1 from that sample size, our degrees of freedom is 22. And so we go through and line up the row with 22 degrees of freedom with the column that has an area to the right of 0.95. And we find here that 12.338 is representing the chi-square critical value for this hypothesis test. Let's jump back. Okay, so we've got our our critical value now stated. We can go through and calculate the test statistic. We calculated a test statistic very similar to this. In number 5 on the handwritten assignment, you use that formula, the chi-square naught, equals the n minus 1 times the sample standard deviation squared divided by the population standard deviation squared. Or you could say n minus 1 times the sample variance divided by the population variance, all coming from the problem's sample standard deviation s and the null hypothesis's sigma being this 0.006 value. So in going through and computing, we find that the chi-square test statistic is 11.229, which is less than 12, and so it's going to be to the left of 12. And so we see here that this test statistic, whoa, Artemis, crazy kitty. We've got our chi-square value is equal to that 11.299. And we see here that since it's in the critical region, we are going to go through and reject the null hypothesis. And so since our claim was the alternate hypothesis, and we are rejecting the null, then we have sufficient evidence to go through and support this claim that the standard deviation has decreased at this level of significance. Now, I was also asked on this problem, though, about the p-value. And so for the p-value, it's the area beyond the test statistic. So I'm going through and illustrating that on the second distribution. And we have here that on the chi-square distribution, so the same as the chi-square distribution above, if we were to just look at our test statistic, that 11.299, and this being a left-tailed test, we want to look at the area then to the left of this test statistic. The area that we have here is equal to the p-value of this problem, the p-value represents the probability of obtaining a test statistic at least as extreme as this one. Now, we can use StatCrunch to go through and figure out this value. I have gone through and I have a video shared in the video description here, just to another YouTuber going through and answering how to use StatCrunch for the problem. I also want to show you another way we can figure out that area as well. On the graphing calculator, it's okay if you don't have one of these. StatCrunch is capable of working it out as well. I've reached out to 3 different Pearson reps to try to get my StatCrunch working, and I still don't have it working for some reason. But the video will show you how to do it in StatCrunch. If you are using the calculator, though, there's this vars button, but above it's the distribution. So if you go second vars to bring you to the distribution menu, and then we scroll down and we use this function, we have chi-square CDF, and it's going to ask us for a lower limit, an upper limit, our degrees of freedom. And in this problem here, the chi-square distribution, it starts at 0, so our lower limit, we're starting at 0, and our upper limit, so where we want the area to stop, is at this 11.299. We have 22 degrees of freedom, because we subtract 1 from the sample size of 23. If we go through and work this down to hit paste, let's see, if you have an older graphing calculator, you need to punch it in this way here, where you have your lower limit, comma, your upper limit, comma, your degrees of freedom. Older calculators, you just punch it in directly this way. They don't have the menu to punch everything in. And when we compute this, we get 0.02978, which if we were to go through and round that to 3 decimal places, we would be getting that 0.030 value that they have listed here. And again, I'll also go through and list the StatCrunch video in the video description, so you can go through and review the way of doing that in StatCrunch. So please keep emailing me questions here, and once I have a few more questions, I will go through and create another video for everyone to review. All right, thank you.